very much. Welcome, everybody. I'm delighted to be here. And my role at Airbus is the central coordination of our quantum technology activities. We have seen a huge growth in the last years of our activities in different areas. I will focus today on one specific of those topics we are tackling. This is quantum communication enabled by space. So I will present the recent results of our teams working there and show you how quickly this topic is moving towards an operational system. So to start, we have heard this morning from Isabel a global view on why quantum technologies are important for aerospace. And I think there are a couple of key messages. And one of them is that in particular for aerospace, all of the different quantum pillars are highly interesting. So we expect a huge impact coming from quantum computing, from quantum communication, and from quantum sensing as well. That's why we are exploring all of them. We have a variety of use cases, a variety of activities. And what I think is always important to understand is that they are not separated from each other. So think about a quantum computer. We also learned this morning that fault-tolerant quantum computing is still far away, or might be far away, but we all have seen, and I think this conference will be another testimonial for that we have extreme progress on the hardware side, on the algorithm side, recently also a lot on the error correction side, error suppression, error mitigation. So the amazing things are happening. And it's clear that we are moving towards an era where the quantum threat comes closer, but also, and I like to call this the quantum opportunities. So I hope, and I'm quite sure we will discuss much more in the next years, when there are fault-tolerant quantum computers, what can we do networking them? What are the most driving use cases? And this links then, or brings quantum communication and quantum communication infrastructure into the game. And that's why it's also not very surprising why so many institutions, companies, and governments are looking into quantum communication infrastructures. And in particular in Europe, the European Commission has a long-term vision for quantum cryptography on the one hand side, but also for quantum information networks. And we in Airbus, we have been involved since quite some years now with them. We are working very closely to develop such a system in Europe. And this is the focus of what we'll tell you today. We have started with a study called COSAC in 2020, where we defined the overarching system architecture for such a secure communication network. We were then working with them both on the terrestrial network side, and we continue to do so. We are, for example, part of the French national quantum communication infrastructure on the terrestrial level. And as an aerospace company, we are heavily involved in the space segment area. And here we are working, for example, with the European space agencies, but also with our national space agencies. And we were able also from our side to put in about 10 years of upstream research now into those programs. And this really helps to advance them very quickly. And we are actually targeting to bring such a system in 2027. Oh, sorry, I would like to go back. In 2027 into orbit, exploitable as a service. So this might be one of the quantum technologies which will be really available for us as an end user providing a new capability. When we talk about quantum communication infrastructure, and I'm happy that I had Andrew already talking a lot about that beforehand, then it's always about sending photons through quantum channels. And this quantum channel needs to be able that we can detect the photon and the properties of the photon at the end of the channel. So fibers are excellent tools for that, allowing for very high key rates. We have seen some of the numbers, but there is, and you have seen this also, there is, due to scattering in the fibers, an inherent length limitation. This is about 100 kilometers, maybe a few hundred kilometers, but to come to a global network, we need free space QKD. We can, for example, use satellites, which already give us the global coverage. However, satellites have a low key rate. So what we do is we take the best of both of those worlds. We take the terrestrial component for the high throughput and the space component for the long range and global coverage. And you can see here that Airbus has positioned itself quite strongly in the different parts of the EuroQCI. We are involved on the network control level, on the key management layer, on the terrestrial side, and we are targeting the space component, the space segment, so the spacecraft, the ground segment, and also the user segment. I will focus today on the space segment side. And if we talk about space QKD, then there are two main protocols which are typically used. The first one we call entanglement-based QKD. Here we are placing an entangled photon source on the satellite. And we have two optical systems who take care that the two photons are transmitted to the respective ground stations. And that's a really intriguing solution because even the satellite doesn't know the key. And we can also use this in the future for quantum information networks because we share entanglement between two sides. But this comes at a cost. And the cost is that it's a large system. You need two optical terminals, and those terminals are really big. And the key rate is low. And the reason is that we need to have a successful transmission of the photons in two channels, or in these two channels here at the same time. And the probabilities of the success multiply. So there's another protocol, prepare and measure, where we have only one QKD source, and we establish a link with one ground station first. Then, subsequently with the second one, we also transmit some classical information via an unsecured channel. And via post-processing, we can establish a secure link on ground between the two ground stations. If you look at the right side at the prepare and measure protocol, what is obvious is that this is not a real-time service, but the keys to communicate, they are stored, and the space segment has the job to take care that we never run out of keys. We can always communicate sufficiently. And this is then the link to the user segment. So the user need, you can imagine that you have a global network of different ground stations to be connected, and the links, the color of the link indicates the number of keys which we need for our communication. And this translates then into what we call a key demand matrix. So a matrix where you have all the mutual entries with the key material needed to do your communication in an operational system. So now we need to design a satellite system which can meet those needs. And what we are doing is, or what we have been doing is we have developed a very complex QKD simulation environment. And you can already guess that not many of the photons from the satellite arrive at the ground. It's maybe only a fraction, maybe every 1,000 photons can arrive, because there are many losses. One of the losses is just the optical impairment of the system. So the telescope at your ground is just smaller than the beam you get. But there are also atmospheric effects, absorption, cloud cover, pointing errors, and very importantly also turbulence effects, which we can at least partly compensate using adaptive optics. But even if the photon arrives at the ground, we need to be able to distinguish it against all the environmental photons. So we have heard that the terrestrial centers are always in cities, and there's a lot of light pollution, which we need to consider. We have the sun, we have the moon, and since we are talking about a single photon level or a few photon level, even the satellite reflections itself is something which we see in the performance of the overall system. So when we put all of this together, we end up with a key rate, and this key rate is time dependent because the satellite moves, and all these input parameters I just mentioned are changing. So what we need to do, we need to employ now a scheduling algorithm and include this and combine it with an overall mission planner for an operational system. And this is how such a QKD system looks like in action. You see a satellite, you see a circle around the satellite, and the circle indicates all the accessible ground stations from a geometrical point of view. And this mission scheduler has information about real-time information on the data, so it knows which of the ground stations are not accessible. It also has the key demand matrix and knows which keys to be generated. And now we have an optimization algorithm to make sure that the right station is connected. So you see we establish a link, then we write the buffer into the memory, we continue the passage, we establish the next link, etc. If we do this, we can simulate the operational performance of a QKD system. And it turns out, and that's something what you probably guess, going from a demo where you have a ground segment and you have a satellite passing at clean sky, perfect conditions, to have an operational system is a huge degradation in performance. So we've survived in the end with something like 5% of the overall performance when we go to an operational system. And we have to design a satellite which is able to compensate for that. And this tool turns out to be exceedingly useful because we can now specify the equipment. We can explore all the various options and see which one is working, which one is operationally efficient, and which one is cost efficient and has low development risk and short development times. So this is really a tool where we can do a lot of trade-offs. And the core message I would like to convey is that the main thing you have to do is to make sure that you are not losing photons. So don't discard photons. And if you do the trade, you end up with a high capacity satellite concept. So we are going to a low Earth orbit, about 500 kilometers, to large apertures, about 50 centimeters. And this allows us to make an efficient satellite system. And this is actually not so bad news because we can reuse a lot of the technology bricks to be developed from other missions, which are already space proven. So one of the really core challenges are the optical terminals. These are highly complex systems, very difficult to build and to also space qualify. And Airbus has two product lines for optical terminals. We have one product line for intra-satellite links, up to 15 centimeter aperture, and another one for optical feeder links, so ground to satellite connections with 25 up to 50 centimeters. We are planning to mount such a terminal on one of our Earth observation platforms. Those platforms, they are optimized for high resolution imaging. So the platforms are capable to target one point of Earth and to do high resolution imaging for a longer passage of the orbit. And so that's exactly the same need we have for a QKD system. And then we need to combine this with quantum technologies. We are developing in-house a space qualified, a space quantum QKD source. We are targeting here a rate of about 1 gigahertz. And this also seems to be the limit for synchronization of the emission from the satellite to the ground segment. And here on the right side, you see how the satellite system looks like. You see here the 50 centimeter aperture, the QKD source, and all the electronics and the pointing systems there included on this part of the satellite. So this is really a high capacity satellite which we are proposing. And it gives us a lot of flexibility on the ground station side. And that's actually important. We are targeting here apertures between 40 and 80 centimeters. But we have shown that even if we have only a 20 centimeter aperture, we can receive on a reasonable rate keys. And we believe that this is very important because you can now think about rooftop options, which we are currently developing, transportable options. And the main point here is that today we don't really know who will use those QKD systems. And we believe having a high capacity satellite with a, let's say, smaller ground segment capability will offer QKD as a service to more end users in the end. I think it's very important when we start such a system to offer this capability. So now I would like to show you a comparison of the performance. So how performing is the system? And so as a reference, we are using a space mission, which was a scientific mission called MISSIUS. It was launched in 2017 by Chinese teams. And it was a great success demonstrating for the first time QKD for space. And what we see when we compare the satellite system, what I've just presented to you, with the MISSIUS system, then we can see on the link level a performance of more than a factor of 200. So we can transfer more than 200 times the key. We can increase the key rate by more than 200 times. But even more interestingly, on system level, so the end-to-end capability, if I have a given demand for keys, for example, over a year, how many satellites do I need to fulfill this need? We see an increase of more than 700 in performance. So one of those satellites you see on the right side would need equivalently 700 satellites of a MISSIUS type. And I think this is one of the messages I wanted to bring to you, that I think that shows that kind of impressively how much we have moved on the last years, and how much this has moved from a demonstration mission now to something what could be an operational service. And we are targeting here, as I said, a launch in 27. So this is not very long anymore in the future. So let me come and wrap up a little bit what I wanted to say. So we believe that quantum communication will be among the first applications which will really come to an operational usage. QKD could be one of them, maybe even in this decade. I've shown you a satellite concept which we have developed. We believe it's the right one. It's a high-capacity satellite, 50-centimeter aperture, about 500 kilometers. It is about 700 times more performing on a system level than the scientific mission, and it paves the way towards an operational usage of QKD. Thank you very much.
So we still have a few minutes. Would you like to take some questions? There's one over there, please.
700 times improvement on the Mesius key rate.
Not on the key rate, on the system performance level. So the key rate is about 200 times larger. We can go back to that.
I see.
And the system level, I can also explain why the system level is even much more than that.
Okay. So I was going to ask, what are the main factors which contribute to that improvement?
Yeah, you see this here. So there we have, let's say, breaking down this into 3 different areas. First of all, we are using an approved satellite concept, and just having a large optics provides, of course, a benefit, because the large optic allows you to better focus on the ground station. And then we also have improvements on the source side, which are quite significant. So we can just generate a QKD pulses at a higher frequency rate. And the detection has significantly improved. So an important part of this improvement is really coming from these amazing developments which we have seen over the last years. What is maybe interesting then is to see the jump from 200 to 700 on system level. And this is essentially coming from the fact that in an operational system, and this is essentially what we need to take into account, there are always situations where you want to transmit keys, but the situation is not perfect. And if you have this high capacity payload, you can still use it, you can still transfer keys, where, let's say, a payload which is rather small and not so performing, it cannot be used in the best way. So basically, we use this high capacity to exploit all the difficult situations in an operational environment.
Thank you.
Any other? Yes.
So this is just sort of a basic question, but at the altitude that these satellites are traveling, how much time do you have to track them as they go from horizon to horizon? How quickly do you have to slow your ground?
Okay, this is now a geometric quick calculation, but let's say you have 100 minutes for one orbit, and then you can say, it's maybe a few 10 minutes you have them in your sight. But you have always, what you have to think of is you need some time. There's of course a classical beacon which makes sure that you can really connect, which is also doing the pointing operationally. So classically connect them, then you optimize the pointing, and only if this is all optimized, then you start with the key transfer. And so when you go back to this, I don't know why it's not starting. When you go back to this picture here, then basically what you can see is there's always some time needed before we can establish the key. And then if you look at this in an operational sense, and this is quite difficult, then you might run into a cloud-covered area, and then you use the link directly. That's why it's so important to really look at this on an operational level.
Thank you.
And there was a question in the back.
How soon might it be before you launch a untrusted entanglement-based satellite?
That's a very good question. So we are currently elaborating on that. So essentially what the main challenge is, there are currently developments for entangled photon sources for space. So we believe on the source, we should be able to do that also in a shorter time frame. And we can also basically reuse the terminals, which I've just shown to you, for such a demonstration mission. The problem will be that the performance is lower. So I think what is currently the challenge is really to think about what is the best demonstration use case you would have. Technically, I don't see a big issue, despite that it's a larger satellite and it's more costly. I rather see currently the issue that we need to converge on the, let's say, first demo application for that.